Okay, thank you very much, Shazia, for inviting me here and also for the very nice introduction. It's my great pleasure to come to UQ and give this talk. UQ for me is like my second home city in Australia. I visited UQ back to 2008, and I'm very, very familiar with the researchers here in the very strong discipline in data science. And I also welcome students and researchers in UQ to visit UNSW, and we'll be happy to host your visit. So today I'll talk about structure-based large-scale heterogeneous graph processing. I'll talk about its applications, challenges, and solutions. This is a shorter version of a tutorial talk we delivered in SIG mode last year. So from this title, you can see there are actually three keywords. One is heterogeneous graph. What is heterogeneous graph? Why it's important? Why do we want to study heterogeneous graphs? The second is structure-based. So there are many different angles, perspectives to look at heterogeneous graph from mining perspective, from learning perspective, and we'll look at it from the structure-based processing and analytics perspective. The third keyword is large scale. So we'll see when the graph data becomes really large, and sometimes if it's dynamic, then it poses great challenges for us to provide real-time analytics response to the analytic tasks. So next, let's begin. The first question is, what is heterogeneous graphs? Or sometimes it's also called heterogeneous information networks, or HIN in short. So traditionally, when we learn graphs in your course, like algorithms, data structures, when we learn about computing the shortest distance, we talk about computing the minimum spanning tree. In those courses, we actually don't worry about if the node has a particular tab, or if the edges, one edge is different from the other. So in this talk, we'll refer to these traditional graphs as conventional graphs or just a regular graph. And HIN, differently, is motivated by real applications, some novel real applications recently. And it considers the applications where we not only have graph data, the data in the network structure, but also we want to differentiate the different types of vertices and also the different types of the edges. And a very simple example here is a DBLP network. It is also a typical example used for illustrating HINs. So if you consider you search your DBLP page, right? And in DBLP network, there are different types of entities or different types of data we are interested in. There are author information, right? And the venue information, which conference, which journal this publication is accepted by, and also what is the topic of this paper, and also where the conference is held, in which country, which city. So we can see if we want to model these novel applications, the traditional data is no longer sufficient, and we need a more flexible, more powerful, more expressive type of data. So this is heterogeneous graphs. And similarly, in social networks or in some user rating database, we can also very naturally see data in the heterogeneous graph model. And also knowledge graph. Knowledge graph, I think many of you are familiar with this. It also can be considered as a special type of heterogeneous graphs where we don't use, introduce very soon, we don't use a meta path to connect different entities, but we can use something like a triplet to connect the entities in knowledge graph. It's considered as a special case of HIN. So this is a typical HIN example. In this DBLP data, we have the author information, we have the venue information, we have the conference information, and the topic information. We have different object types, and also how we connect these different objects together. This is through the data structure, a special metadata called MetaPath. So this basically specifies that an author writes a paper, and this paper is published in the venue, and also this paper has a particular tab. This is how different tabs of vertices are connected. And also there is a special type of HIN, and also along this research direction, there are already a very systematic study of different research topics along this direction. It's called the bipartite networks. So in HIN, general HIN, we can have arbitrary number of different vertex types. And in bipartite network, differently, it specifies there are two types of vertices that we are interested in. So bipartite networks have been widely studied in sociology and in biology. And recently we see, like in the e-commerce, applications, there are very large scale of data modeled as bipartite networks, such as in Amazon, in Taobao, or in eBay. So this is a bipartite network between a user and the product. So in a bipartite network, typically we are not interested in the connections of the vertices of the same type. So for instance, in this application, we are not interested if two users are somehow connected in social network or in a work environment. We are not interested in that. We are only interested in the connections of vertices across different types. Like whether a user has purchased a product, if the user has rated a product, or if a user has browsed the page of a product. In this, we form in this application, you can imagine how many products in these e-commerce platforms, how many different users in these e-commerce platforms. That's in billion scale, and this form a very large scale of bipartite graphs. And why we are interested in this, analyzing this large scale bipartite graph data, because it will help us to understand the behavior of the data in order to mine the value from this data to support decision making in the e-commerce platform. I'll use some examples later to illustrate this. And the focus of this talk, as I mentioned, will focus on structure-based heterogeneous information network processing, and I will categorize it as bipartite graph and general heterogeneous graphs. And in the structure-based HM processing, basically, we talk about the subgraph-based processing and the path-based processing. Subgraph-based processing includes various different cohesive subgraph models, most of them starting from cliques. We know clique is a very fundamental concept in graph theory. And also because of its very restrictive definition, requires every pair of vertices to be connected. There are lots of relaxed models of clique, and I'll introduce them and also discuss their different applications in different sectors. And for the path-based processing, we'll look at reachability, query or cycle detection in HIN, and how this can be applied in the real-life scenarios to make more sense from the large scale of data. And the challenges like subgraph computation, like clique computation, I will introduce very soon, the call-based distribution. So these models have been studied for over 50 years and with tens of thousands of papers. So even in the WLDB conference last week, there are around 10 to 20 research papers focusing on focusing on subgraph computation over graphs. And I noticed the posters in our PhD school. There are also the posters from different groups across different universities in Australia. They also study a similar problem. These subgraph-based analytics, they are crucial for building and optimizing the graph databases and graph computing platforms and support a wide range of real applications. These have been very well studied over conventional data. And where is the gap in the research is that as most of existing works, models, algorithms, computing platforms, paradigms, they focus on the traditional data or the homogeneous network without considering the different types of vertices and edges. So these models and algorithms, they cannot be directly applied to HANs. So we need to develop new models and algorithms for the novel heterogeneous graphs. And here is a high-level summary of applications, structure-based analytics over heterogeneous information networks, and I'll introduce them in detail one by one. So as we just introduced, we can collect very large-scale bipartite graph data just from the e-commerce platform. This is at billion scale, and you can imagine in Amazon or in Alibaba or in eBay, there are different users joining all the time. There are different products posted all the time. There are different user transactions all the time, right? This bipartite graph is no longer large in scale, but also dynamic in updates. So in such a large scale dynamic graph, if we want to mine some particular model, we want to compute some particular model from this network is extremely challenging. And also in these e-commerce platforms, in their tasks, like for fraud detection or for recommendation tasks, they usually require real-time responses. So we not only need to deal with very challenging data, we also need to provide them with real-time response. So this is a real-life application called farm clicking actions. Farm clicking actions is like in the e-commerce platforms. If you consider you own a shop, you want to establish a shop in eBay or in Amazon. So you want yourself to be visible, right? And how can this shop be visible is to improve the rating of your shop, to improve your the credibility of your products, of this owner, and of this shop. And how can you quickly establish that? Is to receive lots of positive ratings from the users, right? And how can we do this? So some smart shop owners, they would hire some fake buyers. Fake buyers meaning that these buyers, they do not actually make the transaction to pay the money. What they do is that the sellers will hire some fake buyers, and these buyers will rate these products. And the sellers will not send anything. There is no actual transaction happen. But the only purpose of this is for the fake buyers to give very high ratings. And also the sellers will need to pay cost to these fake buyers. This is similar to the crowdsourcing we just introduced this morning. We need to pay them. They are not, these fake buyers, they don't come without any cost. So for the sellers, for them, in order to effectively, quickly increase the rating of their products, of their shop, they will hire some fake buyer and request this fake buyer to leave a positive result for as many products in their shop as possible, right? So what will happen after this farm clicking action? So if the seller hires some fake buyer, hire a group of fake buyer, then this will form a very unusual dense subgraph in this bipartite network. So in actual real-life network, actually the graph tend to be quite sparse. But in this bipartite graph, if we identify a subgraph is particularly dense, so this can be suspicious. It is not for sure, but we can detect this suspiciously dense subgraph and hand it to the platform for further investigation. So this is, in this example, it will be very helpful if we can quickly identify this dense subgraph, which is actually a clique, like every vertex from the upper layer is connected with all the vertices in the lower layer. So this can be the potential fake buyers, and these are the products they wish to promote. And as I just introduced, what are the challenges? The challenge here is we have buyers and products at the scale of billion scale. The data size itself is in billion scale. And the number of edges is even larger, right? So because one user purchases more than one product, the number of edges is even larger. And the data is highly dynamic. So in the Alibaba platform, they have some festivals to promote their revenue income. So during those festivals, the data can be updated at tens of thousands transactions, meaning tens of thousands new edges coming into this bipartite network per second. So the solution for this is that we model this dense subgraph as backlick, and aim to very efficiently retrieve this backlick at sub-millisecond scale. We're talking about sub-millisecond scale to efficiently detect them on this bipartite graph to minimize the loss of the e-commerce platform. And the solution lead to nearly 40% improvement in the accuracy and several orders of magnitude improvement in efficiency. So this is where the paper was published. It's a joint work between UNSW, UTS, and the Alibaba Group. It received the Best Paper Run-Up Award from WellDB in 2020. So here is another quite interesting application, also in collaboration with the Alibaba Group. So if we consider this more general form of the network formed in this e-commerce platform, so we have different entities. For instance, the items the user purchased, and the user accounts, the accounts of the user, and where this user visited, and how this user makes payments or transactions. So this form a quite heterogeneous network to capture how the transaction or how the money runs from one type of vertex in this network to another type of vertices. So in this network, if we can identify some irregular patterns, that will also be very helpful for the platform to detect fraudulent behaviors. For instance, if we see if there is a transaction from one user, it goes across several different accounts and then come back to this user. So it forms a cycle. And if it forms a cycle, what does it mean? So the money in this user, it goes out and then goes back again to this account. So this is a typical money laundering behavior. So if some money is illegal, but if it goes around this network and then come back, it becomes legal. It's washed. So in this kind of heterogeneous dynamic network, if we can quickly identify this kind of cycle, that is also very interesting, very important task. And also in recommender system, that is a very, very, very important task. And how can this structure-based analytics help with recommendation? So again, if we continue with this user and product network, for instance, we have users. They rate, in this example, we see a user connected with a movie if this user likes a movie. So if we identify certain types of subgraph in this network, and this could actually mean that if it's a dense subgraph, meaning this, for instance, like U4, U5, U6, and V5, V6, V7, this is very densely connected, meaning these users, they share similar interest of movies, right? Share similar interest of movies. So in this sense, if we have this information in hand, we know users U4, U5, and U6, they like similar types of movies. And how the platform, the e-commerce platform, can leverage this information. So for instance, if this U6, if this user also likes another movie like Wall-E, then if we recommend Wall-E to the other two users in this subgroup, these two users will very likely also enjoy this movie, right? They will purchase this movie or purchase this product, and this will highly improve the effectiveness of recommendation in this network, in this application. And also, when we prepared this tutorial, we had a survey of applying cohesive subgraph model or subgraph-based analytics in other areas, and we find actually in many other disciplines, especially in biology, in chemistry, and in sociology. So this subgraph structure, cohesive substructure, are very widely used. So this is a paper from Nature Physics in 2018. So what 8 model is the bipartite graph from the animal, the co-dependence relationship between animals and plants in a mutualistic ecosystem. So these animals, like bees, butterflies, they carry out the pollination behavior over some plants like flowers or some vegetables. So this is actually, if there is an edge between a bee and a flower, it means that this bee relies on this flower for food, and this flower also relies on this bee or butterfly for pollination for this flower to survive. And in this ecosystem, if this ecosystem is quite dense, it means that one species of butterfly, they have multiple sources of food, and also for the flower, they have multiple choice to carry out pollination. So this ecosystem is quite healthy. But if there are some bees extinct or the flowers extinct, then this bipartite graph will become sparse and sparse. And in this paper, the biologists, they actually use a Keiko model, which I'll introduce very soon, to model this process. And their conclusion is that this cohesive substructure-based analytics over this bipartite graph, this coexistence bipartite graph, is very accurate in identifying the changing point in this ecosystem when this ecosystem becomes dangerous, where all the species in this ecosystem are at the risk of extinction and require human intervention. This is another application. And also in analyzing the disease spread, like the current COVID virus spread. So it's very important to find, we often hear that in the early days of COVID, we often hear that some person is a super spreader. This person spread the virus to a large population. So how these people become a super spreader? So this is a paper back to 2014. They studied this how we identify the potential super spreader in among the population. And the conclusion is that using some cohesive subgraph-based metrics, such as the K-shell number is similar to the K-call number, and this is actually a more accurate indicator compared with the traditional degree or page rank based metrics. For instance, we look at the first figure here. There is a node A. Its degree is high, but its call model is not that high. Another user, its K-shell model is also high at 200. The second user, its degree is high, meaning that this K-call number actually measures how closely, how engaged this user with all other users in this network. For the second user, its degree is also high. It's connected with many neighbors in the network, but its cohesiveness level is not that high at 97. And the third user, its degree level is low, very low compared with the first two, but its K-call model is quite high. And this figure, it illustrates how much to which extent this virus is spread from this user. And from user A, high degree, high call number, it spread to a large portion of the population. The second user, degree is high, K-call number is low. It only spread to a smaller number of the population. And the third user, even though its degree is low, but its K-call number is high, it also spread to a large portion of the population. This indicates strongly that the cohesive subgraph-based metrics are a better indicator to identify the super spreaders when we study the spread of disease and identify the influential nodes in a network. So degree, page rank are no longer the most accurate metrics in these applications. So next is the outline of my talk today for the technical point. So first I will introduce the models for cohesive subgraph over homogeneous or general graphs. And then we'll see existing works, how these cohesive subgraph models are extended from general graph to bipartite graph and the more general types of heterogeneous graphs. So let's start with conventional cohesive subgraph models. So conventional cohesive subgraph models, I think most of them, they stem from the clique model. Clique model, that's very basic. So basically in this subgraph, we require any pair of vertices to be connected. It's a complete graph. And because of its restrictiveness, then many relaxed models are later proposed. Let's look at them one by one. The first is K-call model. K-call model is proposed, we can see it's back to 1966 in a journal on mathematics. And this K-call model has been very widely used in sociology in the past half a century. So it's a basic. This is a K-call model is it has an elegant linear time computation algorithm, and also it's quite powerful in capturing the engagement of users in a network. Its definition is like if it's a K-call, basically this subgraph, we require every vertex to have a degree of at least K. So it imposes a constraint over the degree of vertices. So this is a very simple model. And if we put it in the context of social network, if a user has a degree of at least K, basically this means that in this subgraph, every user has at least K friends, right? Has at least K friends in this subgroup. So if you consider you want to form a group of friends going to gym together, or you want to organize a party at home. And to send out these invitations to form this group, you want everyone to feel engaged, right? If there is one person in a group, if this person has only one friend or only a few number of friends, it's likely that this person will leave this subgroup. So basically this model captures the level of engagement of a user in this subgraph. Every user has at least k friends. The degree of a vertex is at least k. So it has several important properties. It's very fast and easy to compute. So for instance, if we want to compute a 3-core in this graph, very simple, we just remove all the vertices whose degree is smaller than 3. And by the end, we can reach the 3-core subgraph in this example, which are in dark red in this example. And the k-core its size is linear to the size of the graph, even we want to store, to index all the results of the k-core subgraph. And is scalable to very large scale graphs. And this is the example I just introduced. So for instance, in this studying k-core is important because it reflects some very intrinsic values in the social networks. And actually, this core model has been studied after it's proposed in 1966. It's mostly studied by sociologists. And you know, the term social networks does not only refer to our current very large scale platform like Facebook or Twitter. It's back to several decades ago, the sociologists, they have this term social network already. And they study the data, not at a very large scale, but they want to study how a social group or a small social network, how they collapse, or how this social group is formed, is very coherent, is very engaging. So k-core model has been studied by sociologists for a very, very long time. And why the computer scientists become interested in this model is because of the advent of the large-scale modern social networks like Facebook, like Twitter. And in around 2005, there was actually another social platform called Friendster. Friendster, around 2005, it was much, much more popular compared with Twitter and Facebook. It has more, in orders of magnitude, more users compared with Facebook and Twitter. But now no one knows about, no one uses it. It collapsed. And why it collapsed? Computer scientists want to, the sociologists, they want to study it. Computer scientists also want to study it. And the k-core model has been a very powerful tool to study the cohesiveness of the social networks. And the computer scientists are interested in this because the scale of the data has become too large for the sociologists to handle. The sociologists, before, they consider a social group of around several users, tens of users, but now we have billions of users. So sociologists, they can no longer handle this data. So this is where the computer scientists step in to study the k-core-based model to analyze the structure of the modern social networks. The computing of the k-core, as I just said, is very simple. So if we want to compute the 3-core, we iteratively remove or peel the vertices that do not satisfy this degree constraint, and at the same time we update the degree of the neighbors that have been removed, of the vertices that have been removed. For instance, we remove all the vertices with degree 1 and update their the degree of their neighbors, and we continue this, remove the vertices of degree 2, and by the end we can get this 3 call. Very simple. Its complexity is linear to the size of the graph, because in this whole computation we touch the vertices, the edges at most once, so its complexity is linear to the size of the edges in the graph. So this is the first model. First model for the K-call model. It considers the engagement level by imposing a constraint on the degree, number of degree of the vertex. The second model is called K-truss. K-truss is also a model basically mostly used for analyzing social networks. And the K-truss model different from K-call. K-call is from the vertex point of view, from the user point of view. But K-truss, it looks at the strength of the connection between two users. So how is K-truss defined? K-truss is defined by considering the number of triangles that an edge is contained in. So let's consider if an edge is contained in a triangle. So in social network, what does this mean? One edge connecting two vertices is contained in one triangle. This basically means these two users of the two ending points of this edge, they share a common neighbor, right? They share a common neighbor. And this, if we put it in the context of social networks, it means two users or two friends, they share a common friend. So the more triangles this edge is involved in, is contained in, it means the more common friends these two endpoints, these two users share. And this also measures the strength of the connection between these two neighbors, right? So two users, for instance, two users in the social network, they have 100 common friends. Then it's unlikely that these two people will lose contact with each other. But if two users, they have only one common friend, then it's very likely that these two users are not very familiar with each other and easily lose apart. So this K-truss also has some very good properties like polynomial time computation for K-truss. Similarly, we remove the edges that do not satisfy the constraint, the strength constraint. And also, the K-truss we can decompose the graph following the K-truss model and form a hierarchical decomposition of the graph. And K-clique, this should be the most fundamental one. Like K-clique is basically a group of K vertices, such that each pair of the vertices are connected. This is the most cohesive. If we allow there is at most one edge between two vertices. We don't allow multiple edges between two vertices. Then this basically is the highest requirement on the density or on the cohesiveness of a subgraph. We require all of the vertices in the subgraph to be computed. It's the most cohesive model, and computing, listing all the K-cliques, enumerating all the K-cliques, is a NP-hard problem. And its decision version is the famous 21 NP completed problem. And the K-edge connected component, so it looks at this from a different angle. So it wants that the graph to be, or the subgraph computed to be robust or to be connected. So it requires that this subgraph should remain connected even after we remove any K-1 edges. So from its definition, you can imagine it will have important applications when we want to design a robust, a resilient network, such that it can If it's a communication network during war, then even if some connections are cut off, then the whole communication network is still connected. So it means we allow some redundancy, but we improve the robustness of the network. And the densest subgraph. Densest subgraph is also a fundamental definition. So the density of the subgraph is measured by the number of edges divided by the number of vertices. And the larger the number, the denser the subgraph. And in some cases, identifying the densest subgraph is highly important. For instance, in the social media, if there is some bursting events, then usually the retweet, the like, will form a dense subgraph, and we can use this to quickly detect if there are some emergent events happening in daily life. So these are the models of the cohesive subgraphs over the conventional data. And the next question is how can we very naturally extend them to support the novel heterogeneous graphs, and make use of data, to mine the value from the novel data types like bipartite graphs or heterogeneous graphs, to support all the applications like we just mentioned, to make use of the model and make use of the data. So let's first look at the basic definition of a bipartite graph. Bipartite graph, we introduced that there are two layers of graph. Sometimes we call it upper layer and the lower layer. Sometimes we call it left layer and the right layer. But basically, in bipartite graph, we are only interested in the edges connecting these different type of vertices. The edges are connecting vertices on the same layer, like whether U0 and U1, these two users, whether they are friends, we don't care. It's not important for this particular application. So this is the definition of bipartite network. And in bipartite network, so you may consider if we want to extend the very basic K-call model to bipartite network, what should we do? So remind you that the K-call model is defined based on the degree of vertices in a graph. If it's a K-call in the subgraph, we require all the vertices to have a degree of at least K. That is the definition of K-call. So if we want to extend it to bipartite graph, how can we do that? How can we extend it to a bipartite graph? Bipartite graph, here we have two layers of vertices. Its structure is different. There are no connections among the vertices on the same layer. So here a very straightforward solution is because we don't have because we don't have a solution for bipartite network yet, but we have a solution. We have a model which is very effective over general homogeneous graph. So we can solve this unknown problem, to a known problem, right? So if we can convert this bipartite network to a general graph, to a homogeneous graph, then we can solve this problem, right? This is a very intuitive solution. So the first problem is how can we convert this bipartite network to a homogeneous network. So this is one way of the projection. So in the middle is the bipartite graph. This is the bipartite graph. And if we want to convert it to unipartite graph, to graph with only one type, right? But we don't have the connection information of the vertices on the same layer. They are not directly connected, but they are connected through another vertex in the opposite layer, right? So for the upper layer, like 1, 2, 3, 4, if we want to establish the connection of the vertices on the upper layer, we can see if like 1 and 2 are connected through, if they share a common neighbor, simply put. Like 1 and 2, they can be connected by traversing only one vertex across the opposite layer. Then we consider them as connected. So in the projection, we add one edge to connect 1 and 2. And similarly for 1 and 3, they are connected. But for 1 and 4, because they are not directly, they cannot be directly connected through one vertex in the opposite layer, then there is no edge connecting them. So using this philosophy, we can convert this bipartite graph to a unipartite graph. And because there are two types of vertices in bipartite graph, so we can have two different unipartite graphs. One is for the upper layer, and the other is for the lower layer. So there are quite a few work using this philosophy, using this framework to convert bipartite graph into a unipartite graph, and then solve the structure-based analytics directly over the projected unipartite graph. For the unipartite graph, the homogeneous graph, we already have solutions for cohesive substructure-based analytics. We can directly apply them. But yeah, what's the question? Yeah, this is an excellent question. It's very smart of you to ask this question. This directly linked to the disadvantage of this approach. If we use this approach to convert this two type of vertices graph to unipartite graph, then we lose information, right? So for instance, like just asked by the student, like B and C in this graph, they are connected with they are connected actually with different vertices. Like B is connected with 1 to 2, C is connected with 1 to 3. But here in this graph, if we convert it into a unipartite graph, this information is lost. We cannot restore this information. We can no longer restore this information. This information of how this connection happened between two different types of vertices, this information is lost. And then we conduct the analytics based on a compromised result graph, unipartite graph. Then the result will also be compromised. This is the first disadvantage of this projecting-based approach. The second disadvantage is that if this bipartite graph, if it's dense, let's consider if it's dense. If, for instance, there is m vertices in the upper layer and n vertices in the lower layer, in an extreme case, if it's a clique, like all the vertices in the upper layer is connected with the vertices in the lower layer, then in this bipartite graph, we have m times n edges, right? But after the projection, what is the number of edges in the result unipartite graph? After this projection, if upper layer we have m vertices, lower layer we have n vertices, because this bipartite graph is a clique. So every two vertices in this upper layer will be connected. So there will be m squared plus n squared edges. And this size inflation is also significant. So this is not, this means that this projection-based approach is actually not a desirable approach to analyze bipartite graphs, even though it will provide us with a solution, but it has these two major disadvantages. So this means when we want to extend this model when we want to extend the very successful K-core model to also support similar applications over the bipeptide graph, this novel bipeptide graph, we need to make some modifications to adapt to this new data structure of bipeptide graph. And this adaptation should take into consideration the unique characteristics of bipeptide graph structure. So in bipeptide graph structure, what is unique? The unique part is that it has two different layers, right? Two different types of vertices. And in unipeptide graph, it imposes a degree constraint uniformly to all the vertices in the graph because it has only one type of vertices. So in bipeptide graph, it has two types of vertices. And sometimes these two types of vertices are of different semantic meaning. So in order to adapt to bipeptide graph, we can simply impose different degree constraint over these two different types of vertices, right? So we can require that in the upper layer of the bipeptide graph, it should have a degree of at least alpha, and in the lower layer of the bipeptide graph, it should have a degree of at least beta. So this model is called the alpha-beta core model. And in the K-core model over traditional graph, it has some very nice property we just introduced. It has a linear time complexity. It has a hierarchical structure if we compute a different K value. So if we extend it in this way to bipeptide graph, can we still retain these these nice properties? So luckily, if we extend it like this way, we can still retain these properties. For instance, for the online computation problem, we impose different value of alpha and beta over upper and lower layer, but we can still conduct a peeling of this bipeptide graph, just the same as computing for the K-core model. And its time complexity is still linear to the side of the number of edges in the bipeptide graph, because each edge we touch it at most once. And the second question is in the K-core model, we have a nice hierarchical structure. Can we still have it over the bipeptide graph? So a hierarchical structure means that a K-core subgraph is always a supergraph of a K plus one core. The higher value the K, the smaller the size, but it always has this containment relationship from the larger K value to the smaller K value. So basically, the whole graph is a zero core. We don't impose any degree constraint over the vertices. And if we impose the degree constraint like a one core means that we remove all the isolated vertices. We remove all the vertices which are not connected to any other vertex with a degree of 0. Then we have the one core. And the two core, we remove the vertices with degree smaller than 2. And in alpha beta core, we can still retain this property. It still have this hierarchical containment structure. And this hierarchical containment structure, why it is a good property is because as we introduced in the bipeptide graphs, the graph size can be very large. If you look at a billion scale graph, if the graph is at billion scale, even you conduct a linear time complexity algorithm is not good enough. It's not good enough. You scan a linear scale graph will also take you several seconds or over 10 seconds. That is not acceptable in the real applications, which will issue different queries simultaneously at a large number, and also request a fast response. We are looking at have a solution at milliseconds, or even microseconds. And in order to support that, the online computation algorithm from scratch is not good, is always not good. And we need to have pre-built index structures. If you have a pre-built index structures, it means for some questions like a K-call, you can have an optimal solution. Means that you only access the result.